On February 13th, 2023, in the dead of night, a particle crossed the Mediterranean Sea, traveling at nearly the speed of light. It passed through 300 kilometers of solid, water-equivalent material as if it were not there. It entered the KM3 detector, a partially built neutrino telescope sitting 3,500 meters below the surface of the sea off the coast of Sicily, and left a single blue streak of light inside the instrument, a signal so brief it lasted only the time it takes for light to cross the width of a human hair. The scientists who were monitoring the detector data did not know what they had found for months. When they finally reconstructed the particle's path and calculated its energy, the number they got back stopped the entire collaboration in its tracks. The particle carried 220 PD electron volts of energy, 220 quadrillion electron volts, more than 10 times the energy of any particle of its kind ever previously measured. Red on Earth. For reference, the most powerful human-built particle accelerator, the Large Hadron Collider at CERN in Geneva, can accelerate protons to energies of about 13 tera electron volts, roughly 17,000 times less energy than the particle that just swam through the Mediterranean. Something out there in the universe had fired this particle at Earth, something so powerful that it made every particle accelerator human civilization has ever built look like a child's toy. And the object that scientists now believe most likely fired it is the most powerful thing that has ever been confirmed to exist in the observable universe. It is called a blazar. And understanding what it is, how it produces energy on this scale, and why it is pointed directly at our planet is a story that reaches into the deepest physics of space, time, gravity, and matter, and comes back with answers that are more extreme than anything science fiction writers imagined. To understand what a blazar is, you need to start with what lives at the center of almost every large galaxy in the universe, including our own Milky Way. Sitting at the heart of most massive galaxies is a supermassive black hole, an object of such extreme density that its gravitational field prevents even light from escaping once it crosses the event horizon. Our own galactic center contains a supermassive black hole called Sagittarius A, with a mass approximately 4 million times that of our Sun. That sounds large. By the standards of what you need to produce a blazar, it is relatively modest. The most powerful blazars are powered by black holes with masses ranging from hundreds of millions to tens of billions of solar masses. Black holes so massive that if you place them at the center of our solar system, they would engulf every planet from Mercury out through Jupiter and still have room to grow. Around these supermassive black holes and galaxies billions of light years away, vast quantities of gas and dust spiral inward in a structure called an accretion disk, a rotating, heated disk of infalling material that glows brilliantly across every wavelength OF light as the gravitational energy of the infall is converted to heat and radiation. The inner edge of the accretion disk, where the material is hottest and most compressed, reaches temperatures of millions of degrees and shines more brightly than the combined light of every star in the galaxy around it. This combined structure, the supermassive black hole and its blazing accretion disk, is called an active galactic nucleus, or AGN. A and D AGNs are the most luminous persistent objects in the universe, but some AGNs do something that makes them orders of magnitude more extreme than others. The physics of how magnetic fields behave in the intensely rotating, enormously magnetized region just outside a spinning supermassive black hole can, under the right conditions, channel a fraction of the infalling material's energy into two narrow focused beams of plasma, jets of charged particles and electromagnetic radiation, accelerated to very close to the speed of light and blasted outward from the poles of the black hole's rotation axis. These jets are not just bright, they are the most powerful sustained energy outputs in the universe. They can extend for millions of light years into intergalactic space, longer than the diameter of many galaxy clusters. They carry magnetic fields, relativistic electrons, protons, and radiation, and they interact with the intergalactic medium at their ends in enormous lobes of radio-emitting plasma that spread across distances that would take light millions of years to cross. Every type of AGN with a jet pointed somewhere else in the universe, a quasar, a radio galaxy, a Seyfert galaxy, is one variety of this phenomenon. A blazar is the most extreme variety of all, and what makes it extreme is simply geometry. A blazar is an AGN whose jet is pointed almost directly at Earth. That geometric alignment changes everything about what we observe from Earth. When a jet of plasma traveling at 99.9% of the speed of light is pointed almost directly at you, the same relativistic physics that makes a supersonic aircraft sound different depending on whether it is moving toward you or away from you operates on the jet's emission. The light emitted from the jet is Doppler boosted, compressed and amplified by the jet's motion toward Earth in the same way that a supersonic aircraft compresses the sound waves in front of it into a shock wave. The result is that the intrinsic brightness of the blazar's jet already the most luminous thing in the universe by a significant margin, appears hundreds or thousands of times brighter than it would if it were pointed away from us. A blazar can outshine the entire galaxy that contains it by factors of thousands. The most powerful blazars ever detected have luminosities between 10 and 100 trillion times that of our Sun. In 1 second, a powerful blazar emits more energy than our Sun will produce across its entire 10 billion year lifetime. And that energy arrives at Earth across every wavelength of the electromagnetic spectrum simultaneously. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays in a multi-wavelength display that no other object in the universe can match. The blazar, most recently confirmed as the most powerful object ever discovered, is S0528-PLO134, a designation that sounds mundane but describes something almost incomprehensible in scale. Located in the constellation Orion at a distance that puts its light travel time at several billion years, S0528-PLO194 contains a close binary pair of supermassive black holes, two black holes orbiting each other, each one itself of extraordinary mass, together generating a combined accretion and jet system that outshines every other AGN in bolometric luminosity. A study published in the journal Astronomy and Astrophysics in November 2024 by researchers analyzing long-term monitoring data across multiple wavelengths concluded that the emission power from S0528-134 exceeds that of all other known active galactic nuclei, including 3C 4M54.3, which had previously been considered the most extreme object in the gamma-ray sky. The combination of the binary black hole system's orbital dynamics, the shared accretion disk that forms around both black holes as they approach merger, and the geometrical alignment of the jet system toward Earth makes it not only the most luminous blazar known, but potentially the most powerful emitter of gravitational waves among all known AGNs, waves that are currently propagating outward from the system toward us at the speed of light, expected to be detectable by next-generation gravitational wave observatories as they arrive. The particle that crossed the Mediterranean in 2023 arrived from a direction consistent with a population of blazars, and the 2026 analysis published in the Journal of Cosmology and Astroparticle Physics by the KM3-NET collaboration makes the strongest case yet for blazars as its origin. The particle is named KM3-230213A, the designation recording the detector, the year, the month, the day, and a sequential identifier. It is a neutrino. Neutrinos are among the strangest particles in the standard model of physics. They have almost no mass, so little that the combined mass of all neutrinos in the observable universe is only a few percent of the mass of all visible stars. They carry no electrical charge, which means they feel no electromagnetic force and do not interact with ordinary matter electromagnetically. The only forces they respond to are gravity and the weak nuclear force. And the weak force, as its name implies, is extraordinarily feeble in its effective range. A neutrino can pass through a light year of solid lead without interacting with a single atom. The Earth itself is essentially transparent to them. Billions of solar neutrinos pass through every square centimeter of your body every second from below, having traveled through the entire bulk of the planet without noticing it was there. They are, in the vocabulary of astrophysics, ghost particles. And the ghost particle that arrived on February 13, 2023, carried 220 peta-electron volts of energy, a number so large that it challenged every model of how cosmic particle accelerators produce high energy particles, and forced scientists worldwide to rethink what kinds of astrophysical objects can reach energies this extreme. The KM3-NET detector that captured it is an extraordinary instrument in its own right. The Kilometer Cubic Neutrino Telescope, or KM3-NET, is being built in two locations in the Mediterranean Sea. ARCA, off the coast of Sicily at a depth of 3,500 meters, optimized for detecting high-energy astrophysical neutrinos, and ORCA, off the coast of Toulon in France at 2,150 meters, designed to study neutrino oscillation physics. At full completion, ARCA alone will instrument a volume of 1 cubic kilometer of Mediterranean seawater with approximately 200,000 photomultiplier tubes, devices so sensitive they can detect individual photons of light. When a neutrino of sufficient energy does interact with the water or the rock below the detector, it produces a secondary particle. In the case of KM3-230213A, a muon that travels faster than light moves through water. This produces Cherenkov radiation, the optical equivalent of a sonic boom, a blue cone of light that propagates outward from the muon's path and is detected by the surrounding photomultiplier tubes. From the pattern of light detections, which tubes lit up, in what order, at what brightness, scientists reconstruct the direction the muon was traveling and calculate its energy. The muon produced by KM3 230213A traversed the entire detector, activating more than 1/3 of all active sensors. It arrived from a direction that required it to have passed through approximately 300 kilometers of water-equivalent material, which, at that oblique geometry, made an atmospheric origin essentially impossible. This was not a particle produced in Earth's atmosphere. It came from outside, from deep space. Calculating the energy of a particle from the light it leaves in a water column detector involves substantial uncertainty. The energy reconstruction of KM3 230213A carries an uncertainty of roughly a factor of 3 in either direction. The central estimate is 220 PeV, but the true energy could plausibly range from about 110 PeV to 790 PeV. Even at the lower end of that range, it is by far the most energetic neutrino ever recorded. The previous most energetic neutrino detected by IceCube, the competing neutrino telescope buried in the Antarctic ice sheet, had an energy of approximately 6 PeV. The KM3 230213A event is at minimum 18 times more energetic, and at the central estimate is 37 times more energetic. The fact that this event is so far above the rest of the detected neutrino population is itself scientifically remarkable. Either the particle came from an exceptionally powerful source that rarely fires particles at this energy and just happened to fire one in our direction in 2023, or there is a population of sources that routinely produce neutrinos at these energies, but we have simply not detected enough of them yet to build a statistical picture. Both possibilities have profound implications for what kinds of particle accelerators the universe contains and how they work. The Blazar connection is where the two stories, the most powerful object ever discovered and the most powerful particle ever detected, converge. Blazars are natural particle accelerators operating at scales that no human technology can remotely approach. The jet of a powerful blazar, driven by the rotational energy of a spinning supermassive black hole extracted through magnetic field interactions, accelerates protons and electrons to energies that dwarf anything achievable at the LHC. Those ultra-high energy protons, traveling through the intense radiation field inside and around the blazar's jet, collide with photons and produce secondary particles, including pions, which decay into muons and neutrinos. Because neutrinos interact so weakly with matter, they escape the blazar's environment completely unimpeded, traveling in straight lines across billions of light years of intergalactic space without being deflected or absorbed, and arrive at Earth carrying essentially the same energy they had when they were produced. They are, in a very real sense, perfect cosmic messengers, particles that carry information about the most extreme environments in the universe, delivered directly from the source to Earth without any degradation. Every high-energy neutrino that arrives at a detector like KM3NET is a direct message from wherever it was born. KM3 230213A is a message from an object operating at energies beyond what any previous astrophysical observation could document. The 2026 paper by the KM3NET collaboration that traced KM3 230213A to a likely blazar origin used a sophisticated simulation framework called AM3 to model what a realistic population of blazars should produce in terms of neutrino flux at Earth. The simulations adjusted two key physical parameters: baryonic loading, which describes how much energy protons carry relative to electrons in the jet, and the proton spectral index, which determines how the proton's energies are distributed. When the simulations used baryonic loading values and spectral indices within the physically plausible range for powerful blazars, the predicted neutrino emission from the blazar population was consistent with producing events like KM3 230213A at the observed rate. The study does not identify a specific single blazar as the source of the 2023 event. The directional reconstruction of the event gives a 90% confidence circle 2.2 degrees in radius on the sky, which contains many potential source candidates, but the population level analysis is consistent with blazars as the class of objects responsible. 3 separate research groups published papers in 2026 exploring different aspects of the KM3 230213A event's possible origin, one suggesting a primordial cosmogenic origin, where the neutrino was produced by a proton colliding with a photon from the cosmic microwave background, another suggesting a transient source, such as a gamma-ray burst or a tidal disruption event, where a black hole shreds a star, and the third supporting the blazar hypothesis. As of April 2026, the true origin of the most energetic neutrino ever detected has not been definitively resolved. That unresolved question is itself one of the most important open problems in astrophysics. If KM3 came from blazars, then blazars are accelerating particles to energies that require a complete re-examination of the physical limits of jet-based particle acceleration around supermassive black holes. The standard models of Blazer particle acceleration had difficulty explaining how protons could be boosted to the energies needed to produce a 220 PeV neutrino. Getting there requires either a magnetic field far stronger than standard models assume, or a much larger jet region in which particles accumulate energy through repeated scattering, or some combination of both, none of which are ruled out by existing observations, but all of which push the standard model of Blazer physics into territory that has not been well explored. If instead KM3 230213A came from a cosmogenic process, a proton at even higher energy produced somewhere in the universe colliding with a cosmic microwave background photon, then somewhere in T-He universe, there is a source of protons at energies above 100 eV, energies so extreme that they define a region called the GZK limit beyond which protons cannot travel more than a few hundred million light years without being absorbed by background photons. A cosmogenic origin for KM3, or 23022113A, would imply a source of ultra-high energy cosmic rays within a relatively local volume of the universe that has not yet been identified. The broader context of this discovery is messenger astronomy, the emerging scientific discipline that combines observations of gravitational waves, neutrinos, cosmic rays, and electromagnetic radiation across all wavelengths to build a complete picture of the most extreme events in the universe. The detection of KM3's 230213A is the highest energy entry in the growing catalog of astrophysical neutrinos that KM3NT and IceCube are assembling together. When KM3NT reaches its full design volume, still several years away as construction continues, it will be sensitive enough to detect neutrinos at these energies at a rate sufficient to build a statistical sample rather than relying on single extreme events. The combination of ARCA and ORCA, together with IceCube and the planned IceCube Gen 2 upgrade, will give neutrino astronomy a detection volume large enough to begin systematically mapping where in the universe the most energetic particles are being produced. And the blazers that are the leading candidates for producing those particles are themselves being mapped in unprecedented detail by the Event Horizon Telescope, the planet-scale radio observatory that captured the first images of black holes in 2019 and 2021, which is now being extended toward higher observing Cygnus X1, captured stunning new insights into how black hole jets are launched, adding a direct local observation to the theoretical picture that the Blazer results are forcing scientists to revise. What all of these threads add up to is a picture of the universe that is more violent, more extreme, and more creative in its physics than the models built on Earth-based observations had anticipated. Blazers were predicted to be powerful. Their actual power, confirmed in the energy of a single particle that crossed the Mediterranean in the early hours of a February morning and left a blue streak in a partially built underwater telescope, exceeds what the standard models could comfortably explain. The most powerful object ever confirmed in the universe is a binary pair of supermassive black holes firing a relativistic jet at Earth, across billions of light years, with a luminosity that makes our sun look like a candle beside a nuclear explosion. The most powerful particle ever detected arrived from somewhere in that direction, carrying energy that no earthly accelerator could produce, as a ghost that passed through 300 kilometers of ocean without noticing and registered itself in a single blue flash at the bottom of the sea. The universe has been speaking to us in particles for billions of years. We only just built the instrument to hear what the message said. And what it said, in the energy of a single muon on February 13th, 2023, is that the objects producing it are operating at a scale of power that physics is still learning how to describe. The total energy output of every nuclear weapon ever built by every nation on Earth combined, the entire accumulated arsenal of the Cold War, the hydrogen bombs, the city destroyers, would not account for a single millisecond of the energy a powerful blazar releases in its jet. The sun, which has been fusing hydrogen into helium continuously for 4.6 billion years and will continue for another 5 billion, produces energy at a rate that the jet of the most powerful blazar exceeds in a fraction of a second. The closest human analogy for what blazars do does not exist, because nothing in human experience or history operates at anything close to the scale. The universe contains objects that are not just larger than anything human civilization has built, they are larger than anything human civilization can meaningfully visualize or intuitively grasp. The confirmation of S0528-134 as the most luminous and powerful emitter ever cataloged, and the detection of a particle from a blazer-like source carrying 220 peta-electron volts across billions of light years of intergalactic space are not just astronomical discoveries. They are a recalibration of what the universe permits. A reminder that the physics operating at the centers of distant galaxies is not the physics of human experience. It is something else entirely. And we are only now, with the instruments humanity has managed to build and deploy in space and on ocean floors and in Antarctic ice sheets, beginning to hear what that something else has to say,